Okay, YouTube, in this video I'm going to run through a couple more quick examples on how to solve some logarithmic equations using our properties of logarithms and inverses in order to find solutions. So let's go ahead and get started over here on the left. Letter A, it says 3 times log base 4 of 6x equals 9. Okay, so again, when you're talking about solving logarithmic or exponential things, but in this case specifically logarithmic things, before we can undo or use inverse properties, what we want to do is we want to isolate the logarithmic expression itself. So log base 4 of 6x, we need to get this by itself. In order to do so, we need to get rid of this 3. So the first thing we'll do is we'll just go ahead and divide both sides by 3. And so we get those to cancel out. We say log base 4 of 6x is equal to 9 divided by 3, which is 3. So in this case, we've got our logarithmic thing isolated. So in order to undo this log, we want to exponentiate both sides, or in other words, use the inverse of a logarithmic thing, which is an exponential thing. We just want to use, or we would like to exponentiate both sides using the same base as our log right here. So what we'll do is we'll say, okay, so now everything on the left will say 4 to the power of everything on the left is the same thing as 4 to the power of everything on the right. So again, I'll write this a little bit cleaner. We say 4 to the power of log base 4 of 6x is equal to 4 to the power of 3. So what we end up with here is essentially our 4 and our log base 4 canceling out, and we get 6x. And then 4 to the power of 3, the cube of 4 is 64. We say 6x equals 64, and we could say, well, we'll split this 6 ways. It seems to me the same as 32 thirds, and this would be very, very easy to check by plugging back into the original expression and seeing that they actually do come out to be equivalent, these two sides of the equation. Now, letter B over here actually uses a property of logarithms that basically denotes that the sum of two logs with the same basis. Now, I want to point this out. These are both the common logs, so we didn't write a base there, but we just automatically assume these are 10. So since I have, two logs with base 10, and I'm adding those, we can rewrite this as the product of their arguments. That is, let's write this off, maybe down over here a little bit. We say log of x plus log of y, and in general we say log base a of x plus log base a of y is the same thing as log base a of their product. So we say x times y, and so or u and v, we could say this is u, this is v, and so u times v. I just say u and v now because I realize we're dealing with x's up here. So we could say like this is like our u, this quantity here, and this is like our v. But we could rewrite this as a condensed logarithmic expression. That is, take this sum and rewrite it as the product. So we say log of just the product of x times x minus 9. Okay, and this is equal to 1. And the convenient thing about this is now we've got the logarithmic expression isolated. So we can now exponentiate both sides. In this case, we're going to exponentiate with base 10 because that is the base of our log. So we say 10 to the power of log base 10. Those things cancel, and we are left with simply x times x minus 9, and this is equal to, now on the right here, 10 to the first, so we get 10. So now solving this, you might notice that this is going to turn out to be a second degree polynomial, but we say, okay, so x squared minus 9x is equal to positive 10. We need to set this equal to 0, so we get x squared minus 9x minus 10 equal to 0. Okay, so let's see if I've done my math right here. We say two numbers that multiply out to be. So now that we've got this factored, we can set each factor equal to 0, and we end up with x minus 10 equals 0. Let me change my brush size here, maybe down to 5. Or x plus 1 is 0, and therefore we get x equals negative 1 and positive 10. So now one word of warning, and this is a good example to go through for a few reasons. One, because we get to use this fun property of sums and products with logarithms, but also because when you end up with two solutions for a logarithmic expression, which by the way our original logarithmic expression, let me rewrite it here because we've gotten kind of messy over here. We say log of x plus log of x minus 9 was our original expression. This was equal to 1. we should plug these both into the original equation and check them, since we got more than one answer, especially also because one of these was negative. The simple fact of the matter is this: when we attempt to do this or plug it back in the original equation the first time through with -1 here, we say log, if we plug -1 for x, we say plus log of -1 minus 9 is equal to 1. We end up with log of a negative number, which first of all is not even defined, because you couldn't take 10 to the power of something and end up with something negative, essentially, and 10's are log base there. But also, you know, we have log base 10 of -10, which is it's just nonsense to say something like that. So this 1 right here, we actually give it a name, okay? And this is referred to as an extraneous, base word here, extraneous solution, which basically means it worked out algebraically when we solved a quadratic thing, but when you plug it back into the original logarithmic expression, it doesn't work. So now what if we tried to plug 10 back in? Okay, so we'd say log of 10 plus log of 10 minus 9 is 1. And 10 is going to work here, but we say log of 10, well, log base 10 of 10, that's just 1, plus now log base or 10 of 10 minus 9, so in other words, log of 1, well, special property of logs is log of 1 is always 0, and so we get 1 plus 0 equals 0, which definitely checks out. So just a quick video on solving some logarithmic equations.